So, welcome to EPG Pathshala lectures on numerical methods. Now, we are going to talk about systems of linear equations. In this module, we will be doing the introductory part, and then next two modules will be talking about the methods for solving systems of linear equations. Our model learning objectives set for this particular module are: why systems of linear equations, matrices and operations on matrices, introduction to vector spaces, and basics of systems of linear equations. So, these are what we are going to do, because matrices play a very important role in representing systems of equations, and the vector space concepts are being used for vector space concepts are also used to discuss some of the important results regarding systems of linear equations. So, why systems of linear equations? So, whenever you are learning a new topic, the first questions come to our mind is that why should we learn this topic, and basically we are all interested in solving some problems in real world situations, and there these systems of linear equations will appear. The first encounter of the systems of linear equations, because we already done interpolation, was during interpolation itself. So, if you consider the problem of determining the nth degree interpolating polynomial p n x over passing through the given n plus 1 nodes x I y I, reduces to solving a system of n plus 1 linear equations in terms of n plus 1 unknowns, which are coefficients of the polynomial a 0, a 1, a 2, a 3, a n. And this is obtained by conditions this, because what is the condition? Condition is that p n x I should be y I. So, p n x I will be given by this and y I will be this. So, here I know what is x I raised to n x I, and all this is known. So, therefore, this becomes a linear equation in unknowns a 0, a 1, a 2, a 3, a n, and such there are n plus 1 equations, and this becomes a system of n plus 1 equations in n plus 1 unknowns. Some of the illustrations, I mean this is the illustration which shows you how interpolating polynomial determination can be done through systems of linear equation. For example, consider the temperature at a certain point in a function in a furnace at 3 different times are given in the following table. So, we are given the times in second 5, 9 and 12, and temperature in degree centigrades are given as 105, 181 and 263. The interpolating polynomial for this data, say p 2 x, is given because there are 3 points, it will be second degree polynomial. So, it will have a x square plus b x plus c. Those 3 unknowns a, b and c are to be determined, and this we are taking on the interval 5 to 12, because 5 is the least observation and 12 is the next time largest time of the time at which the observation is made. Can be determined by solving the following system of 3 equations. So, what I am trying to do is I am putting t equal to 5 or x equal to 5 in this equation and putting first equation. So, 25 a plus 5 b plus c equal to 105, 105 comes from the table. Then I put 9, 81 a plus 9 b plus c equal to 181, 181 comes from the table, and the third is 144 a plus 12 b plus c equal to 263, and that 263 comes from the table. So, again it becomes solving a system of equations like this. Now, 2 real world applications we will be considering, which you must have done it at your school level even. So, one is mixing problem. So, we have got a chemist wishes to create a 32 ounce solution with 12% acid content. Now, he uses 2 types of stock solutions. So, in the organization there may be already some solutions present. So, we are using 2 from them, and we know the acid contents in these known solutions, and first solution has 30% acid, the second solution has 12% acid, and we want to produce a new solution with 32 ounces solution, 32 ounce solution with 12% acid content. So, what we need to find out is how much quantity of each of these 2 solutions should be used to create this new solution. So, let x is ounces of solution 1 is used and y ounces of solution B is used, then constraint due to the requirement of the quantity will be what? Weight of the solution, that is total weight is x plus y, and that x plus y should be 32 ounce, that is first requirement. And second requirement is acid content, because acid content in the first is 30%. So, I will get 0.3 into x acid, I will get it from solution 1, and 0.1 into y I will get acid from solution 2, and therefore, their sum should be 0.12%, because I want 12% acid content. So, I get this system of 2 equations in 2 unknowns. So, that is how if I solve this system I get the solution of the original problem. This is the third second illustration of real world, and we want to find out the traffic flows. So, here you are seeing that there is a various traffic. So, here incoming traffic is 610, here outgoing traffic I know, here incoming traffic I know, here outgoing traffic I know, here incoming traffic I know, here outgoing traffic I know. But I want to know what will be the traffic on this road, on this road, on this road and on this road, and that I can do it by making an assumption that whatever at each junction, there are junction points A, B, C, D. So, at each junction point what I want to know is what is the incoming traffic, and that much must be the outgoing traffic. So, incoming traffic and outgoing traffic, if I equate at each of these junction, I will get the values of x 1, x 2, x 3, x 4, and for that I am just writing here in this table junction A, B, C, D, and we are considering incoming traffic is 610 plus x 4, outgoing traffic is 450 plus x 1, and I am now subtracting the so x 1 minus x 4 equal to 160. So, when I equate these two equations, I will get equation in the form like this. Similarly, I am doing at junction B. So, incoming traffic is 400 plus x 1, outgoing traffic is 640 plus x 2. You can see it from the figure here. So, at junction B, incoming traffic is 400 plus x 1, outgoing traffic is 640 plus x 2. So, like that you can look at this here, and then again equating this I will get that equation. At C, similarly I will do the same thing, input output, and equating this 2 I will get x 3 minus x 2 equal to 600, and similarly at D I will get x 3 minus x 4 equal to 520. So, these are the 4 equations and in 4 unknowns. So, again I get solving this traffic problem, I need to solve this system of linear equations. So, system of linear equations will appear in many of the mathematical model of the real world situations. So, in this module, some results related to existence and uniqueness of the general system of n linear equations in m unknowns we are going to discuss. So, this is the system of linear equation I am talking about, a 1 1 x 1 plus a 1 2 x 2 plus a 1 n x n equal to b 1, a 2 1 x 1 plus this equal to b 2, a m 1 x 1. So, I am taking m equations in n unknowns. So, the most general system of linear equations I am looking at. Now, the matrix algebra plays an important role in the solution of the system of linear equations, and hence initially basic concepts of matrix algebra will be introduced. So, we are going to introduce matrix algebra concepts. So, an m by n matrix A is a 2-dimensional array of numbers. So, we are just arranging numbers in the 2-dimensional array, and with m rows and n columns. So, there will be m rows here and n columns. So, first row elements I am denoting by a 1 1 1 2 1 n. So, first suffix denotes row number, second suffix denotes column number, and like that I get this particular matrix. C j is a column matrix, because I am getting only one column. So, because there is only one column, I will call this as a column matrix, or this will be jth column vector. So, if I consider C j, so if jth column if I consider, that will be jth column vector, and R I will be nothing but ith row vector. So, if I consider ith row, so second row will be a 2 1 a 2 2 a 2 n, ith row will be a I 1 a I 2 a I n, is called the ith row vector of A. In concise form, A is also written as a I j. So, we just write the a general element of the matrix, and we say that you have to repeat m times, and n will be j will be running from 1 to n. So, an m by n matrix with m not equal to n is called as a rectangular matrix, and if m is equal to n, it will be called as a square matrix. So, m equal to n means number of rows and number of columns is equal, it is a square matrix. Two matrices, now we are talking about operations on matrices. What kind of operations can be performed on the matrices? So, we are doing here, we are taking two matrices Aij, Bij. This is P of order P cross Q, this is of order m cross n. M number of rows, n number of columns, P number of rows, Q number of columns are said to be equal. Now, when two matrices are said to be equal, if their order is same and all elements are identical. So, if they have the same size, that is m is equal to p and n is equal to q. So, number of rows should be same, number of columns should be same, and Aij should be equal to Bij for all I equal to 1 to 3 up to m and j equal to 1 to 3 up to n. Then only we will say that the two matrices are exactly equal. Now, we define addition of two matrices. So, A and B are defined only if. So, addition of two matrices A and B is defined only if these matrices have the same size, otherwise addition is not defined. So, if they are same size means your m should be equal to p and n should be equal to q. So, that is what they should be of the same size, and in that case A plus B will be given by Cij m cross n matrix, and Cij will be nothing but the sum of each individual element. So, element by element we add if the size is same. Then we talk about given real number k, suppose we have got just a constant k, and the scalar multiplication of the matrix A by scalar k, scalar constant, that is this number k, is defined as a matrix k dot A, and that is given by say Cij m cross n, where Cij will be given in terms of Aij and k. So, each element of the matrix will be multiplied by k, each element of the matrix will be multiplied by k, that is your scalar multiplication. So, both these operations addition and scalar multiplication are element by element. Product of the two matrices is again a special operation here we define, and it is defined only if the number of columns of A is equal to number of rows of B. So, in this particular case, if number of columns of A, that is n, is equal to number of rows of B, that is p. So, if n is equal to p, then only product will be defined, otherwise product will not be defined. And in that case, what will be the general element of the product? General element of the product will be given by the ai1 into b1j, ai2 into b2j, ain into bnj. What is this actually? This is nothing but element by element you are multiplying and adding. So, we are taking ith row of the matrix and jth column of the B matrix, second matrix, and we are multiplying one by one element there, and we are adding those products here. So, that will give me the ijth element of this. So, in order to compute ijth element of the product, I have to select ith row of matrix A and jth column of matrix B. You multiply element by element and then add all those products together will give me Cij. You can note that if you consider this as vectors, then Cij will be the dot product of ith row vector and of A and jth column vector of B. So, this will be just dot product of this. Note that the product B dot A can be defined only if q is equal to m, and hence it is possible that though A dot B is defined, B dot A may not be defined. So, product reverse, if you reverse the order of the matrix, product may not be defined. If A and B are any two n by n matrices, then A dot B and B dot A both will be defined, but in general they need not be equal. So, even if the product is defined, it may not be equal, and in many cases the A B is defined, B A may not be defined, that is possible. For example, let us take an example 1. So, what I am trying to do, what is the use of such matrices? I am just illustrating it by a simple example here, that two factory outlets in Delhi and Mumbai sell sofas, I am denoting it by S, chairs by C and tables by T. The sales and profit data of these products at both the outlets in the first half and second half of 2015 is given by the following matrices. So, I am taking first half of 2015, I am calling this as matrix S1. So, I have got one factory outlet, another factory outlet, sofa, chair and table, and these are the actual sales. So, 4000 sofas are sold in at factory outlet 1 in first half, and similarly I am representing second half of 2015 by matrix S2, and the profit matrix I am given that on sofa I got per sofa I get profit as 620, per chair I will get profit of 350 and per table I will get profit of 300. So, that is what I will get these matrices to represent my data, and now I can use this operations to find some of the things here. So, find the total sales for each product for the year 2015 for both the factory outlets. So, if I want to find out total sales at both the factory outlets, what I have to do is I have to simply and second, now the second question is that find the total profit at the two factory outlets in the first and second half of 2015, and see if a company decides to fix up the target for the sales in the first half of the 2016 as 1.5 times that of the sales in the second half of 2015, find the targeted sale figures for each of the products at two factory outlets. You can see that these three are very practical questions which are asked in many industries. And now, solution A will say that total sales for 2015 must be sales in first part and sales in second part. So, S1 plus S2. Now, S1 matrix is given by this, S2 matrix is given by this, these are the factory outlets. So, I have to add these two together, and when I add this together, this is sofa figure, this is chair figure, this table figure. So, addition is term by term, so element by element. So, 4000 plus 3500 is 7500, 600 plus 2600 is 3200, likewise I get that additional matrix, and I will get. So, I can say that at factory 1 what is the total sale is 7500 sofas, 3200 chairs, and like that I can say 4400 tables in the first half, and in the second half at first factory outlet, and at second factory outlet we will get those figures from the second row. So, matrix operations are used to answer the questions here. Now, the total profit I want to find out in the first half I want to find out. Now, this is the matrix I get. So, these are the sales and this is the profit. So, profit per sofa, profit per chair and profit per table, that is the number of sofas sold, number of chairs sold, number of tables sold. So, I have to multiply this by this. So, this is your matrix multiplication. So, if I multiply this and add, so 4000 into 620 plus 600 into 350 plus 400 2400 into 300, and if I add all of them together I will get this figure, and similarly I will get this figure for this. So, this is the total profit in the first half at factory outlet 1 and factory outlet 2. So, that is what I can find out from that, and similarly I can do the same operation for second half. Then targeted sale for the first half of 2016 is 1.5 times. So, 1.5 times targeted sale or already sale done in the second half. So, sale done in the second half is given by this matrix. So, that matrix into 1.5. So, multiply element by element to each of them. So, 1.5 times 3500 is 5250, 1.5 times 2600 is 3900, like that I will get. So, these are my targeted figures for the sofa and chairs in the at the factory outlet 1 and factory outlet 2. So, you can see that this matrix operations will be used in this manner. Now, there are certain special matrices which come in play during our discussion, and those we are discussing first. So, transpose of a matrix. So, you are given a matrix A I J, again M cross N is a matrix obtained by. So, transpose of a matrix A like this is obtained by changing rows of A into columns and is denoted by A transpose. So, if my matrix is say 1, 2, 3, 4, then what is my transpose? Transpose will be 1, 2, 3, 4 like that, it will be like this. So, your matrix transpose matrix will be given by this. So, row first row becomes first column, second row becomes second column. So, this is what we will getting. Alright. So, we will get this. So, the null or 0 matrix is the matrix having all its elements 0 and is denoted by 0. So, if I get 0 0 0 everywhere, I will get 0 matrix. An n cross n square matrix A is said to be diagonal matrix if except diagonal elements all elements are 0. So, if all elements are 0, I will be getting the diagonal matrix. So, that is what I get diagonal matrix, and if I get diagonal matrix the n cross n unit matrix, if I want to define, what I will do? I will be doing it as I n cross n is diagonal matrix with all diagonal entries as 1. So, you can see here that diagonal matrix is like this. For example, if I take 2 by 2 diagonal matrix, if I want, I will get here say 3 4 0 0 is my diagonal matrix. But if I want unit matrix, I will get what? I will get 1 0 sorry 1 1, I will take 1 1 here and 0 0 here. So, like that, this is my unit matrix of 2 by 2 unit matrix, like that we can write down. And then you can see that for any n cross n matrix A dot I n cross n is I n cross n dot A is equal to A. So, if you take unit matrix and multiply this another matrix by that, I will be getting the same matrix. For example, if I take here 3 2, let us write down here another figure. I can get here say 3 4 2 1, and if I multiply by 1 this. So, I will get here 3 2 into 1 0. So, that will be 3. So, I will get this equal to 3 again, then this into this will give me 2 here, this into this will give me 1 here, and this into this will give me 4 here. So, again I get the same matrix. So, the product matrix also you get the same. So, you can see here that this last expression we can verify. Now, we are getting A is said to be an upper triangular matrix if A I j is equal to 0 for all I j 1 to n and I greater than j. So, upper triangular matrix, if I want to write down, I will get all elements when I is greater than j. I is greater than j, I will be getting here, I will be getting here like this. So, 1 3 4 and 0. So, I greater than j. So, I is 1, j is 1, 2, I is 2, j is only 2. So, these elements are non-zero, these are all 0 elements, then I will get upper triangular matrix, sorry, this is lower triangular matrix, and 1 minute. So, A is said to be an upper triangular matrix, say I j is 0 for all I j, I greater than j. So, this one is upper triangular, and lower triangular if I want, I will be getting this as 0 and this will be this. So, that will be lower triangular matrix. So, I will be getting lower triangular and upper triangular matrices like this. Given an n cross n matrix A and n cross n matrix B is said to be the inverse of A if A dot B into B dot A is equal to identity matrix. For example, here if I am given A is equal to 2 1 7 4, then A inverse is given by 4 minus 1 minus 7 2, and because you can see that A into A inverse, I will be getting it as an identity matrix. Why? Because you can see here when I multiplied A into A inverse, that means 2 1 I have to multiply with this. So, 2 into 4 is 8, 1 into 7 minus 7. So, I will get first value as 1, and identity matrix here is nothing but 1 0 1 here 1 here 0 here and 0 here. So, this is what I will get, and therefore, I will get identity matrix like this, and you can verify that this product is going to be this. So, such a matrix is called as inverse of a matrix. So, given n cross n matrix A, inverse of A may not exist. However, if A inverse exists, then it has to be unique. All right. Now, we are talking about vector spaces. So, an n component vector is a one dimensional array of n real numbers and can be expressed as x bar equal to x 1, x 2, x 3, x n, where x 1, x 2, x 3, x n are real numbers and set of all such n component vectors is denoted by R n. I am restricting my definition, I am not taking a general definition of vector space, I am taking vector space R n only. So, that means I am taking n dimensional vectors. So, an n component vector. So, any vector representation is like this. So, these are the components. It is similar to row vector in the matrix. So, x bar equal to x 1, x 2, x 3, x n, where x 1, x 2, x 3, x n are real numbers and the set of all such n component vectors is denoted by R n. Now, any n component vector x bar, that is a vector in R n, can be regarded either as n cross 1 column matrix or 1 cross n row matrix, and consequently I can represent it either as a row vector. If I write it in a column format, I will get 1 by n, and here I will be getting n by 1. So, n rows 1 column. So, that is column vector, and 1 by n is row matrix. So, consequently addition of two vectors x bar and y bar and scalar multiplication of vectors can be defined as just as your matrix multiplication. So, I can say addition will be just element by element addition, scalar multiplication is element by element scalar multiplication, and dot product is nothing but element by element product, and then addition of all those products. So, this is what I will get dot product as. So, the vectors V 1, V 2, V 3, V k in R n now linearly independent, means they are linearly independent if for some real constant C 1, C 2, C 3, C k, this is equal to 0. If I say that if this linear combination C 1 V 1 plus C 2 V 2 plus C k V k is equal to 0, this will imply that C 1, C 2, C k are all 0 elements. In other words, we are saying that if there exists constant C 1, C 2, C k, where some of these constants are non-zero such that C 1, C 2, C k is equal to 0, then these vectors are said to be linearly dependent. So, suppose that this is non-zero, C 1 is non-zero, then I can express V 1 in terms of remaining vectors by taking this on the other side and dividing it by C 1. And therefore, I can say here that thus the vectors are linearly dependent if any one of them is expressed as a linear combination of the remaining vectors. And if I cannot do that, the vectors are said to be linearly independent. Note that if I take E I bar as 1 in the ith position and rest of the elements 0, rest of the components 0, are linearly independent vectors in R n, because if I take any vector x bar, I can write as x 1 E 1 bar plus x 2 E 2 bar plus x n E n bar, because if I write x 1 E 1 bar means I will be getting x 1 in first component and rest of them will be 0. X 2 E 2 bar, because E 2 is second component is 1 and rest of them are 0, therefore, I will get x 2 in the second component, rest of them will be 0, and when you add together I will be getting this vector. So, that means these vectors are such that they are themselves linearly independent, because if I take C 1 two vectors, suppose I take 0 1, 1 0 and 0 1, say 0 1 if I take, then what will happen? 0 1, and if I want to take C 1 plus C 2 times this, if I take C 2 times this, then you will see here that C 1 plus C 2 times this, when I take this will give you this equal to 0 0 vector if I am given. That means C 1 plus 0, that is C 1 is 0 and C 2 plus 0 is C 2 is 0. So, that is how I will get this vector like this. So, therefore, I can get that these vectors are linearly independent of each other. Now, this is called as a basis. When the vectors are linearly independent and if they generate the all elements of the space, that is called as a basis, and this is called as a standard basis for R n. It is well known mathematical fact that R n, any set of vectors V 1, V 2, V 3, V k with k greater than n has to be linearly dependent. That means, in R n any set of vectors, if it is linearly independent, then number of elements must be less than n, less than or equal to n. If it is greater than n, then that set of vectors will be always linearly dependent. So, these are all concepts which are well known in mathematics. You might have learned somewhere some other places also, and therefore, we are quickly revising those concepts, nothing more than that we are doing here. The rank of a matrix M cross n matrix A is defined as the maximum number of linearly independent row vectors or column vectors in A. You know that n by n matrix has n row vectors or n column vectors. Out of that, how many are linearly independent? So, maximum number of linearly independent vectors, row vectors or column vectors, they are going to be identical, and that will be considered as the rank of a matrix. Note that if A is M cross n matrix, then all row vectors of A are in R n and all column vectors of vectors are in R m, and hence rank cannot be more than m as well as more than n, and therefore, rank has to be less than or equal to m comma n. An n cross n matrix is said to be non-singular if rank of A equal to n, and is said to be singular if rank of A is less than n. Okay. So, singular means rank of A has to be equal, non-singular means rank of A has to be n, and singular means rank of A is less than n. So, if there are less number of linearly independent row vectors, then that matrix will be said to be singular, otherwise we will call it as non-singular. So, it is well known that the inverse of an n cross n matrix A exists if and only if A is non-singular, that is rank of A is equal to n. So, inverse of a matrix exists if and only if rank of that matrix has to be equal to n. Find the rank of this matrix. Suppose I want to find the rank of this matrix, then the row vectors are 6 0 4 4, R 2 is minus 3 21 12 12, R 3 is 7 minus 7 0 minus 5. The first two row vectors R 1 and R 2 are linearly independent, as R 2 is not equal to C times R 1. You cannot write R 2 and R 1 as C times this, because if I multiply by any C here, the second component will always remain 0, whereas here second component is 21, and therefore, these two row vectors cannot be expressed in the form R 2 not equal to C R 1. So, therefore, these two are linearly independent of each other. For any real number C, you cannot express that. However, R 1, R 2, R 3 are linearly dependent. Why? You can see that R 1 minus 1 by 3 R 2 minus R 3 will be equal to 0. You just check that R 1 is this minus 1 by 3 times. So, 1 by 3 times this I have to subtract from that, and minus R 3 if I do, I will be getting this as 0, and therefore, these three vectors are linearly dependent. So, the rank of this matrix in that case becomes 2. That is how we can do that. Now, to find out rank, there are called as elementary row operations we can have. In order to compute the rank of a matrix A or inverse of a matrix A, it is convenient to convert the matrix A in the upper triangular form without changing certain characteristics of A. Such a conversion of A is achieved using so called elementary row operations, which are as under. Why we want to take it as upper triangular matrix? The reason is like this. If I want to take an upper triangular matrix like this, so where we get 1, 2, 3, then 4, 5 and 6, and here I will write 0, 0, 0. So, if I convert it into an upper triangular matrix here, then you can see here that this vector is going to be independent of this, because this component is 0. Whatever I see I multiply here, I will never get this as 0, and if I multiply by 0, I will get both of them 0, and therefore, this vector cannot be expressed as c times this, or this vector cannot be expressed as c times this, and these 3 vectors are all linearly independent. If suppose that this becomes 0, then I can say that the matrix has only 2 linearly independent vectors. So, for upper triangular matrix, it is easy to determine how many linearly independent row vectors are there. So, rank of a matrix can be easily determined. Now, to convert rank of a matrix into upper triangular form, what I will have to do is, these are the operations that we can perform. So, interchange 2 rows. If I interchange 2 rows, row vectors are not changing, and therefore, rank will also not change, their linear independence will not change. Multiply row by a non-zero constant c times, if I multiply, the its form does not change. So, multiplying row by a non-zero constant, and add a multiple of one row into another row. These are the 3 elementary row operations that we can perform on the matrix, and that will help us to convert the matrix into upper triangular form and ensure that rank does not change. If a matrix is converted into matrix B by any combination of these operations, then it can be proved that rank of A and rank of B are identical. We use these operations so as to ensure that B is an upper triangular matrix, so that it is easy to find its rank. We will do this illustration here. Say example 3. So, find the rank of A. So, I am trying to find the rank of this. So, I want to convert this elementary row operation, I am going to convert. So, on this I am considering R 2. So, this is R 2 plus 1 by 2 times R 1. So, 1 by 2 times R 1. So, if I multiply by 1 by 2 here, I will get 3. So, 3 minus 3 will become 0 here. So, I will get 0, then I will get 1 by 2 times this. So, 0. So, 21 will remain 21, and 12 plus 2 will give me 14, and 27 plus 2 will give me 29. So, I will get this. Then so what I am trying to do is I am trying to make this element 0. In order to make this 0, I have to add 3 to this. So, I am multiplying this by 1 by 2 and adding. If I want to do the same thing here, what I will have to do? I will have to multiply this by 7 and divide by 6. So, 7 by 6. So, if I multiply this by 7 by 6 and subtract, I will be getting this row by 7 by 6 and subtract from here, then I will get this element as 0. So, I am eliminating my, so these 2 elements I am trying to make them 0. So, that lower triangular part will be 0, and then I will do this same thing. I want to do now this element 0. So, I will divide this by 1 by 3 and add, I will be getting this. So, 1 by 3 plus R 1, if I add, I will get this as 0, but in doing so all the elements have become 0 here. What does that mean? That this rank of this matrix is same as rank of this matrix, but this matrix cannot have 3 non-zero rows. So, number of non-zero rows in the upper triangular matrix is its rank. So, therefore, rank of this matrix is 2. So, I can say that rank of this matrix is 2. Note that the last matrix is upper triangular matrix and has only 2 non-zero rows having non-zero diagonal elements and last row vector as 0. Hence, row vector R 1, R 2, R 3 are linearly dependent as 0 R times R 1 plus 0 times R 2 plus R 3 is equal to 0, and therefore, I can say that R 1, R 2 are linearly R 1, R 2 are linearly independent. First component of R 1 is non-zero, whereas second component R 2 is 0, and thus rank of A is equal to 2. The specific procedure followed in example 3 reduces the matrix A into a specific upper triangular form, in which all non-zero rows precede these 0 rows. So, if exists and the diagonal elements of non-zero rows are non-zero, such a matrix is said to be in the row equivalent form. So, what we are doing is that if in a matrix all 0 rows are or non-zero rows precede 0 rows, and if all diagonal elements of non-zero rows are non-zero, then we consider it as a row equivalent form of a matrix. So, in this module we have considered following points discussed: the relevance of systems of linear equations in the real world situation that we have seen, then introduction to matrices and operations on matrices we have studied, and their use in practical situations. Then vector space R n and concept of linear dependence, independence and basis of vector spaces we have done, and the rank of a matrix we have discussed using the concept of linear independence, and how to compute rank using elementary row operations. So, these are the points we have discussed. In the next module, what we will be doing is how these concepts are used in finding out solutions of the systems of linear equations that we will discuss first. So, we will be talking about the existence and uniqueness results regarding solutions of the systems of linear equations and the methods for finding out such solutions. Thank you.